So we went through this deck a little before, but one thing we talked about was this vanishing gradient problem, right? So if you have a deep network, especially if you're adding, dozens or hundreds of layers, the gradients at every step start piling up. You're basically reducing the size of them each time, and you can get very small gradients, or you can have gradients that kind of, if they're higher than 1, then when they multiply together, you get these numbers that become infinity, and then it's all learning is kind of meaningless. So it's a problem you have to try to avoid, especially if you're a long chain of nodes that's being done in backpropagation. This Inception network was an attempt by researchers at Google to do convolutional neural networks but have more layers, right? So they like the idea of that, as we were showing, right, last class, where you have low-level features and then higher-level features and then very high-level features. They're like, oh, came out even just with 3 or 4 layers. What if we had 50 layers, right? But then they tried it, and then all the gradients are 0, and it doesn't work. So they worked on it, and they came up with Inception is the idea. Google Lanette was the first paper on it, but it's called Inception. And it's got this idea where you've got multiple types of convolutions. So I've got a website that has some nice explanation of this. Oh, maybe I had it in my slide even. So they still have the pooling idea, right, where we're saying take basically a downsampled version of the previous data and create a smaller version, so they're going to have that. And then they have 3x3 convolution, which is normal, and maybe a 5x5 as well. So one question is, what does it mean that these are side by side? And the other question is, what the heck is a 1x1 convolution? So what it means that they're side by side is that, and I will not be able to draw on this now because it's PowerPoint. What that means is that they're basically being added together, right? Concatenated. So they're not being combined or merged. These have their own set of weights, and these have their own set of weights. Can everyone see? Nothing much is changing. It's just my mouse. So there might not be much to see. The screen has changed there, so hopefully people can see it. They're just concatenated together, right? So you have a series of numbers that are the outputs from your layer. Usually we've just got all the outputs of all the response functions from each of the filters, right? And that's your series of numbers. But what if you had another set of filters that were giving their outputs as well? They usually give you different answers, still being convolved across the entire previous data. And it's just another vector of numbers. Maybe there's 100 of these and there's 100 of these. So just concatenate them. Now you have a vector of 200 numbers, and that's it, right? Then you have your max pooling one, which is basically downsampling the previous layer. So maybe this has, I don't know if it would have 100, it might have 25 numbers because it's going to be a smaller thing. And you can concatenate it as well. So they just add it on as a vector and get combined together. So the aspect of the 1x1 convolution, I've got some links to some pages here that have nice descriptions of it. If I can find it myself. Yeah, here we go. Where is it? Oh, I can't see it because I'm full screen. There we go. The idea of, and this is one of the links in that slide there, which I'll post all the slides up after because it's kind of a bunch of them out of order. The idea of 1x1 convolution is just the same as a multi-one, except it's just one number, right? So you've got some neighborhood of, in a 3x3, you've got a neighborhood of pixels that you average together in some way to give you that pixel. And you've got weights combining them all together, so it's not really an average, it's weighted. In a 1x1, you're taking some weight that learns a way to represent or shift the value from one pixel and just get all added together. So you're optimizing a single number, but across all the pixels. So it's still being convolved across the entire image. And it's really a way to let you transform the feature. So it's giving you one weight to modify this output and change it, right? But then you might still have a whole bunch of these filters. So you have a whole bunch of independent weights to let you shift that layer and create it. So it doesn't change the size or anything. It just lets you move the embedding or gives the networks the freedom to basically have some additional convolution on that data to multiply it or scale it or normalize it. But again, you're not saying what it has to do with it. It's just giving it this weight that lets it multiply it. So when they do it this way, I guess they can use for reducing the number of dimensions as well. So they kind of put them in front of these 3x3 and 5x5 convolutions to give it this buffer and reduce the dimensions of it. Oh, okay, we're reducing redundancy because you can get rid of all the RGBs, right? Because the size is the same. It's still 200 by 200. Yeah, so you can basically reduce the number of features, but for every pixel, you're going to basically turning a bunch of the features into one number, and then you can learn a certain number of those. So it's almost like having a manually tunable PCA for some different ways of mapping it. But again, these things were devised not necessarily with a good theoretical reason, but because they worked, and then they're trying to understand what they're kind of doing, right? Yeah, and this other link has like a video of how it works together. Which you can watch. Oh, I don't have you have to load it and play it. But it just shows the idea that they're having, right, just to show it fairly good. Each of these different types of filters is being applied to the previous layer's outputs, right? And so they're essentially a block that's being convolved across the entire image and creating a new vector. But it could go shallow or it could go deep in terms of the number of layers it's composing on, right? So the usual 3x3 ones and stuff go across all the different layers and all the different channels and produce a new box like that. But in the 1x1s, you're taking values from across that image and creating a new channel. But the main approach then is that whatever number of filters you have here, they just get concatenated together. So the new output vector for this Inception module is literally just the vector outputs from each of these filters into a new vector, and that feeds the next one. And so whatever comes into here could be anything. It could be like normal CNN layers. It could be another Inception node. It could be fully connected. You do this kind of splitting out into doing lots of different combinations, and now the new vector that you produce from this has various different patterns and things that it's been looking at, right? It's looking at different sizes of convolutions, it's reducing the size, and it's doing these kind of one-by-one transformations. And so by doing that, then they found they were able to train this thing with basically arbitrary number of nodes, like it has a number of layers, like how deep you want to have the neural network, and they could maintain the gradients because they wouldn't be vanishing. So that's one of the big things that happened with once deep learning started being deeper trying to solve this problem. Another approach that people looked at, is kind of three main ways that I've seen that people have done it. There's this Inception approach. Resnet came out basically at the same time, and it's simpler, but it also shows up now a lot as well. So you often have pre-trained Resnet 50 or Resnet 70 on ImageNet, and you can use those as a pre-trained network because they've trained something with maybe 150 layers deep, right? And you could take the first 50 of it, or even just pre-trained one that has 50 layers, and they've trained it on all of ImageNet for classification, and you can use that as your starting model. That's a common thing people do. So if you say Resnet 50, that's what people are doing. And Resnet basically just takes links from previous layers. So rather than having multiple types of nodes like Inception does to basically spread out what you're learning at every point into different types of things, it almost keeps a memory. It's not memory because we're not about time, but it looks back to a previous layer and takes the signal from there and combines it, but still concatenates it the same way. So you take the vector from 2 steps ago and the vector from the most recent layer and just add them together. So you have a new vector that contains them together, and the new network is going to learn that. So then at every step, the gradient isn't just involved in the data from that layer. It's got kind of a memory and a stickiness across the entire network. And so this seems to help reduce those kind of bugs where everything just keeps converging to 0 or infinity. And it lets you make them quite long. And you could obviously, there's another parameter you could tune, right, is how many steps backwards do you go? Do you go back 1 step or 2 steps? You can still do your pooling and everything. So there's just so many hyperparameters for a CNN like this now, because every one of these numbers is something you could change, and there's no reason to say one's better than another. So you have to just try them. So that's another one. And then the third one, which I didn't have on my slide, so it's on my my browser as another link. Is Densenets. And Densenet takes a similar idea to, this is from Facebook, so I think Resnet was Microsoft, so every company had to have its response. They take the similar idea to Resnet, but kind of take it further. Right, so they show Resnet in their description here, right? So we've got the usual, that doesn't really increase the size much, does it? We've got the usual convolutional neural networks. You've got some image, you've got some filters that are being learned, and whatever is going on in between, they've just abstracted that away to pooling. Resnet takes the output from a previous layer and adds it to the response function at this layer in order to kind of increase stability. So in Densenet, like why add one when you can add them all, right? So the idea of Densenet is you just take all the previous output layers and concatenate them, or many of them at least. So the idea is that it's dense at your node because you're getting the responses from multiple different layers in the past, not the past, from previous layers, so that you're essentially learning a higher level model, but where you don't forget what happened before, right? Because if we think about the original CNNs we talked about with max pooling, we had the lower level features, and then we had a higher level feature because it was only looking at the previous pixels that were downsampled. And the third layer was even looking at a higher level because it was looking at something that had been downsampled and learned multiple times. In Densenet, you say, well, let them see everything, right? So why not let the higher level know about the edge detectors and the eye detectors and the face detectors as well when it's trying to determine something? It's not going to hurt. It makes it a little longer to train because there's more information, but why would you throw it away? And so this helps as well with stability, and it grows quite well. So I've heard people saying that on especially on large complex images, this is much better than Resnet. Resnet's kind of the default powerful thing that everyone uses to pre-train on, so you'll see more Resnet than Densenet, but I've heard people who've used Densenet on much larger image sets like medical imaging, and say that it's actually even better than Resnet. Right? And so one thing you do have to track, and I figure they must have some way of reducing this, is that as you keep going forward, if you're really keeping all the previous layers, you're going to get more and more vectors as you go, right? So the later layers are going to just be enormous number of inputs. So you could subsample them, like randomly pick out some of them, or only take some of the previous layers from previous output layers. But how you do that is, again, another combination choice. Right, so I guess sometimes they do this where they basically force it to go through a very small number of channels to reduce the size so it doesn't just keep growing forever. So that's the other interesting thing that relates with that. Okay. So any questions about that? Let me see if I had this one now is done. Right. We had this one, which is talking about it. I guess, yeah, okay, so they had some results then in this chart. The description of Resnet as well. Just talking about how well they worked, I guess, in different papers at that time on the competition. So how the networks were getting bigger and bigger from 2012 to 2015, and then how the performance was increasing on this classification task. So more layers is better, but this is not always true. So there's people trying to push back for simpler networks as well, to say that maybe adding more layers and just adding more weights is kind of the cheap way to get performance. So trying to build better understood models on the inside so that we can have a smaller number of parameters and get the same kind of performance is actually very interesting research to do. So there's not just trying to always make them infinitely bigger.